Here we're going to look at the Langmuir adsorption isotherm. This is an equilibrium isotherm. And the idea is that we have some solid, in this case, and the solid, if it's adsorbing something, is referred to as an adsorbent. And then we have some component B out here in the gas phase, and some of those B molecules adsorb on the surface. So B would be called the adsorbate. And of course, adsorption is used in a number of processes for separation, also important in catalysis. And the Langmuir isotherm is one of the simpler representations of how the number of molecules adsorbed, which is on the y-axis. It also could be number of grams adsorbed per gram of adsorbent. As a function of pressure, if we're looking at gas phase adsorption, if it was liquid phase, we're looking at concentration. And so the form of the Langmuir isotherm is the amount of B adsorbed, a constant, an adsorption equilibrium constant, and the pressure B. And so this form means that low enough pressures down here, XB would just be linear in the pressure of B. And if we get to high enough pressures, high enough so that this term is large relative to 1, then XB would just be equal to alpha. In other words, you're going to saturate out at some value at high enough pressures. Now the Langmuir isotherm is a function of temperature, and we'll look at a simple simulation now to see what that temperature dependence is. Well, here we're looking at a simulation for the Langmuir isotherm. Now this happens to be a case where we could have two adsorbates, but essentially made one of them 0, so we can look at this total pressure. Then really it's just the pressure of B. And I'm showing a plot of isotherm. And what I can do in this simulation, I can lower the temperature, and notice the isotherm now at lower temperature will approach saturation at significantly lower pressure. And I can also raise the temperature so over this pressure range it's pretty much linear. Correspondingly, instead of lowering the temperature, I could increase how strongly B is adsorbed on the surface, and that then creates an isotherm that is the same behavior as if I lowered the temperature. So the Langmuir isotherm results by a fairly simple assumption, and doesn't mean it's going to apply in most cases, but it's a good first case. And that's just saying at equilibrium, of course, the rate of adsorption is the rate of desorption. That's going to be true. What the assumption is that we can write the rate of adsorption as some adsorption rate constant, the pressure of component B, times 1 minus the fraction of sites that are occupied by B, or this term is the fraction of vacant sites. And the rate of desorption, the desorption rate constant, times the fraction of the sites occupied by B. Instead of fraction, of course, could be the number of sites, and that just changes a constant. So if I just rearrange this equation, I get that the fraction of B is KB pressure B 1 plus KB pressure B. And if instead of fraction I wanted to write it in terms of number of grams, for example, this term alpha would then be in the equation. So you could look at theta as this XB over alpha.